Ambient light is that ubiquitous glow that surrounds us. It's what allows you to see under your desk. You look under your desk right now and you see into the back corner of your desk and you can still see there, even though there's no direct light source that's illuminating the back corner of your desk. Why can you see that? Well, because light rays, photons of light, are bouncing all around you. They're interacting with materials and surfaces, and some of those surfaces are absorbing that light. Some of those materials are reflecting that light, either in whole or in part. And then there are other materials that are emitting light, right? The light itself, but you could have various light sources all throughout your space. That complex interplay of light and surfaces is what creates ambient light. Now, unfortunately, at this time, we don't have the hardware capacity to actually simulate in real time or in interactive frame rate ambient light. We can do some really clever tricks, but the easiest way to produce an ambient lighting effect, and the one that we're going to explore first, is just a single static color that we're going to apply to all of the objects in the scene, and it forms that base for a lot of lighting in rendering games. So this is just this constant light will be present. We can change it, we can modify it over time, and that's what we're going to do in this demo. So open up Visual Studio's Lesson 5.1, take a look at the ambient lighting demo.h, and we'll see the declarations here. The declarations for the vertex attribute are the same as before. We're going to employ the same texturing that we did in the last demos. And so we have a position and a texture coordinate that's associated with each vertex. We have all the same stuff that we had before. The new material that we have is an ambient color location. And if we look at the fragment shader, ambient color location is this guy right here. We have a uniform that we're specifying in the fragment shader. We also had the uniform worldview projection that we specified in the vertex shader. In fact, if you take a look at this vertex shader, it's identical to the vertex shaders from the last lessons. But the fragment shader, we can also include uniform variables. So we have an ambient color uniform variable, and it's a vec4. We need to cache where that location is. So that's what the ambient color location variable is all about. The world matrix for the object that we're going to manipulate. Index and count and color texture, and now we have a new class called light. Let's take a look at that light class real quick, and you'll see that we extend this. Light class is a base class that will extend into different kinds of lights that you'll see in the next couple of lessons. Light is a game component, so it has an update method. We're not going to apply anything in this particular update method, but we could. And all this particular light has is a color. It's a vec4. So that immediately should say, okay, well, I've got a vec4 there, I've got a vec4 here. That's what we're using as input into our fragment shader. So now let's look at the implementation of our ambient lighting demo class. And the implementation says, build those two vertex and fragment shaders. Let's load a sphere model. Let's build a vertex and index buffer from that sphere model. Let's find the location for the worldview projection matrix. And now the new code is find an ambient color location. So go find where the ambient color is inside of that shader program. We're going to load our earthcomposite.jpg. That's that earth texture. It's got some cloud cover over it as well. And we're going to build the vertex array object, the input layout, just as we did in the last lesson. Now, finally, we've got our new light. So let's initialize our new light. And, something that I've kind of been shying away from talking about, and what I'll talk about here is the destructors for every one of those demos. You notice that we're cleaning up after ourselves when we're done here. So when we have like GL gen textures, we need to do GL delete textures. GL gen textures is the OpenGL call that's actually being applied inside of soil load OGL texture. We need to delete the color texture. We need to call GL delete buffers for the index and vertex buffers. That's actually the plural, GL delete textures GL delete buffers, plural, because we can actually delete multiple at a time. So if we had an array of those, we could specify the size of that array and then delete them all in one shot. And likewise for GL delete vertex arrays. So I'm just pointing this out to you that we're deleting our ambient light. We're cleaning up after ourselves. And in our update method, we've got an update ambient light call. Let's go take a look at what that's doing. So every frame, calling update ambient light. And what update ambient light is doing is it's pulling the keyboard. So it's doing a glfw get key for the page up key and the page down key. And what I'm doing with the page up key and the page down key is in the page up key, I'm increasing the ambient intensity up to a value of 1. And I'm decreasing the ambient intensity down to a value of 0 whenever the page down key is pressed. And I'm doing that independent of frame. So this is based on a elapsed time. The ambient intensity is increasing with the time of each frame up to a maximum of the value 1 and to a minimum of the value 0. You'll see this interactively when we show the demo, where the page up key and page down key are changing the ambient intensity. So what does ambient intensity really mean? Well, it just means I'm going to set the color right, to a vec3 of that intensity. And what I mean by that is when I cast a vec3 from a scalar to a vector 3, what actually happens then is we create an RGB channel, a vec3 of whatever the intensity is. So if the intensity was 0, this would be a vec3 of 0, 0, 0. If we had a half intensity light, this would be 0.5, 0.5, 0.5 across all three channels. And then finally, the fourth parameter, we're actually not going to use, but we're going to pass it in as a vec4 with the value 1. We could use it if we wanted to. We could overload that to mean something else. So that's what we're going to do. We're going to set the color of the ambient light. You'll see here in a moment in the draw call how that ambient light gets passed into the shader. You should be thinking, okay, well, I'm going to pass this very similarly to how I passed for the worldview projection matrix, and you're absolutely right. So once we've cached the ambient color location with the GL get uniform location call, now we can update it inside of our draw call with GL uniform, in this case, 4FV, so a vector of 4 floating point values, and we only want one that we're going to pass in. There's a size of one of those, so we're going to pass all of those in, those 4 floating point values, at whatever the location is in the ambient color location cache. That's the long and the short of our code. Let's look at the fragment shader and see what the ambient color actually does now that it's been passed into the fragment shader. We've passed in the ambient color vec4. We sample the color texture just like we did in the last lessons. Use the texture GLSL intrinsic using the passed in texture sampler and the incoming texture coordinates that came from the vertex shader. And now we're going to modify the RGB channel of our output color. So color.rgb, and I want to mention this here in just a second, what this is all about, is equal to sampled color.rgb times ambient color.rgb. So what this is doing is, this is called swizzling. When we use this syntax where we say color dot, we're accessing a member, and there are 4 channels, remember, inside of a vec4. They can be referenced with the member names R, G, B, and A, or X, Y, Z, and W. They mean the same thing. They can't be commingled, but they mean the same thing. They mean the 0th channel, the 1st channel, the 2nd channel, and the 3rd channel. Now, what's interesting about swizzling is that I can combine these things. I don't just have to specify RGB. I could say color.RRR would give me a vec3 that was made from the same channel over and over again for 3 times. So I get a vec3 that was built from the red channel. Color.RGB, and then I'm assigning it says, change those 3 channels to the multiplication of these 2 vectors. And remember, for vector multiplication, what I'm doing is component-wise multiplication. So the passed in ambient color, if you can imagine that the passed in ambient color was 1, it would have no impact on the sampled color. But if it was 0, it would make it all black. We would have no color. And if it was 0.5, then whatever the sample color is, we would be dividing it by 2 for every one of the R, G, and B channels. And finally, we're not going to modify the color channel at all here. We're going to take the color channel directly out of the sampled texture. So that alpha channel, and you will see here in lesson 6, we'll talk a lot about transparency and opacity for color blending. Right now, we could have just, well, ignored this, but let's set this to the sampled texture. Okay. Finally, let's compile this. Let's see the result. So this looks just like our previous example. We've got our sphere. It's mapped with a texture, but this time I'm going to press the page up key and the page down key. And when I press the page down key, you notice that I'm transitioning from 0 to 1 for intensity on the ambient color. All right, so that's the simplest model that we can really do for ambient lighting. There's much more complicated models, but this is a nice start.